Okay, in this video we're going to look at mean drift velocity, and we're going to look at equations associated with it and the concepts associated with it as well. So starting with the equation, I is equal to a NEV. Now I've done something very specific here. You'll notice that I've actually used a small v. The reason I've used a small v is because it's very easy to confuse voltage and velocity. And in this case, we are talking about velocity. A small v represents velocity. So let's just note that on there. So this is velocity. And actually it's a mean velocity of the electrons traveling through the wire when we've got a current flowing through that wire. So that is our current. So hopefully you'll be able to see there that that the current is directly proportional to the velocity. So the current is directly proportional to the velocity, and as a result, we can see this equation. Now you'll see that there are other values here. We've got a, little n, and a little e. So we'll start at the beginning. A is the cross-sectional area of that wire. So cross-sectional area. So that's cross-sectional area of a wire, and just to visualize that a little bit, so that's that value right there. So any wire obviously is cylindrical, so you can expect the cross-sectional area to be pi r squared. Just to remember that there. Next term is n, and it's the number density of free electrons. So number density of electrons. I'm going to come back to that term very shortly. And then finally we have the little e. Little e represents the charge on one electron, which we've come across before, is 1.6 times 10 to the minus 19 coulombs. So 1.6 times 10 to the minus 19 coulombs, and that is a constant in any equation. So that one is a constant. Now, number density of electrons is specific to a material, so unless you're changing material in any equation, this value is going to be constant as well. And the area, cross-sectional area of a wire, you need to remember is pi r squared, like that. So in the next section, what we're going to look at is we're going to look at some of these terms individually and what they mean and where they come from. Right, so we'll start with number density. So in the equation, I is equal to a n e v. N is the number density of free electrons in a material. Now that literally is what it suggests. So if you imagine your wire, you've got all your positive ions which form the central nuclei that make up the material of the atoms, and all around it you've got your electrons, and essentially what the number density represents is a value that is an amount of charge carriers per meters cubed. Okay, that's a volume, so it's the amount of charge carriers per meter cubed. Now what's really important about this is that you can see there are three different types of materials. You've got conductors, you've got semiconductors, and you've got insulators. So you've got those three different types of materials, and the differences are fairly obvious. That this is how we define what these materials are. Now, a conductor is a material that has absolutely lots of charge carriers. Okay, has lots of charge carriers, and in this case, the charge carriers are electrons, so it has lots of free electrons able to move around, which is why metals are great, because metals have lots of free electrons. Semiconductors have less, okay? They still have some, but they have less. And then insulators have very few indeed. So what we're seeing here is that the number of electrons defines what kind of material it is. And in the case of a conductor, your book gives an excellent example of how many a conductor should have. They should have kind of numbers in the realms of about 10 to the 28. Semiconductors, you're looking at about 10 to the 17. And obviously much fewer with insulators. But you don't need to know those numbers. It's just to give you an idea of the difference in charge carriers per meter cubed. Now please remember, N is equal to a number of charge carriers per meter cubed. So the unit for N is meters to the minus 3 as an important unit that you need to remember. So just to recap, number density is the number of charge carriers per meter cubed. Conductors have lots, semiconductors have less, and insulators have very few indeed. Metals being even the better type. Okay. Right, the mean drift velocity. So looking back at the equation, oftentimes you might be asked to work out what V is. So in this case, V is going to be equal to I divided by ANE. And that's a very common rearrangement of this calculation, quite simply because it's a very useful value to find out, because you're finding out how fast the electrons on average are moving through a wire. Now why is it an average value? Well, because if we look at electrons moving through, now I'm just going to represent electrons as negative symbols. Now you're making a very big assumption when you think about electricity, that you think that as soon as you turn on you add your potential difference on your wire, and essentially your electrons then go, oh right, no, I need to move to that positive charge, and you assume they move directly to it. Well, that is not the case at all. They do not do that, because there's lots of other things in the way. Namely, other electrons, namely positive ions. So this is pretty much a really rubbish kind of idea and example. So what really happens in a wire, if we just do a nice zooming in, so we've got lots of positive ions, and we have lots of negative ones as well. I mean, our negative electrons. Now generally they'll move in a straight line until something gets in their way, and obviously you'll study electrostatic repulsion in a lot more detail later on, so some of this theory you'll have to take my word for now. But if we look at how these electrons move, they'll travel in a straight line, and they will essentially bounce around the ions that they are through. So what will happen is they will travel in very, very awkward directions sometimes. Just like that, and they all follow very strange paths. Now, not one of these electrons does the journey in the same amount of time. So they're all traveling in this direction, and not one of these electrons does it in the same amount of time. However, they do cover the same overall distance. And so this is why we use an average value for this calculation, because it would be very, very foolish of us to suggest that when we work out V for the equation, it'd be very foolish of us to suggest that this V is the actual velocity of one electron at any one point in time, because we don't know that. There's no way of knowing the path it's taking or how long it's taking to get there. All we know is that it has to cover a certain distance, and that based on the flow of current and the flow of electrons that we know from the current here, we can assume that that amount of charge flows per second, and then hence that allows us to work out the velocity. And so that's an average or a mean drift velocity of the electrons. Now the word drift is very important also. The word drift is used because they are drifting. They're not being propelled in any way. They're drifting based on the bias of the system that they're in. So you've got to remember that the reason that these are moving is because there's a very large negative charge over here, and there's a very large positive on this side, and they are repelled and attracted to the positive and negative respectively as a result, and so they move, they drift through the wire. Now that doesn't mean that once this electron, say, has moved, that there's nothing there. Believe it or not, another electron will come to take its place. Because it's not just one electron moving from place to place, and that creates work done. It's the whole system. It's all of the electrons in the system at any one point in time are drifting in that direction, and so they're all drifting, and so they're all moving, and it's a bit like moving water through a pipe in many ways. You don't just have one drop of water coming through; you have the whole lot coming through. All of it moves at the same time. So if you have a water piping system, when you increase a pressure from one side, then the pressure is felt on the other instantaneously. And it's the same thing with electrons and moving through a wire. One last thing you should be aware of with this equation is the concepts about the kind of values that you'd be expecting that you would get from it. Now, V especially, we think of electrons as being something that moves very, very fast. And in a free space, it would move very fast. But actually, in wires, they actually move really, really slowly. You're talking times 10 to the -4 meters per second. Yeah, you heard me. Times 10 to the -4 meters per second. Now, what's really surprising about that is a lot of people think that electricity moves instantaneously in a wire, and feel that because when they turn on a light switch, for example, they go, "Oh, the light turns on immediately. Man, that electron was quick traveling from the switch to the light." Well, obviously, as we suggested in the previous question or in the previous slide, that is not the case. It's just the fact that there are electrons throughout, and so when we flick the switch, the electrons where you are at get pushed, and so that push translates all the way down the line to the electrons in the lamp, which then electrons through the lamp start moving, and as a result they transfer work and energy and allow the lamp to be lit. So a very, very important point is that electrons in a wire move very, very slowly. So now that's the content covered for mean drift velocity equation and all the associated values and figures. So I would recommend you having a look at a worked example in your textbook just to make sure you're happy, and we'll have a go at some in class as well.